Hello and welcome to the online BSc program on data science and programming. In this video, we are going to continue from our previous video where we introduced vector spaces and study some properties of vector spaces. In particular, we will build on the axioms that we have seen in the definition of a vector space. So, let us derive a consequence of the axioms, the conditions that are needed in order for something to be a vector space. So, this is called the cancellation law of vector addition. So, if V1 plus V, you have three vectors V1, V2, V3 in the vector space V, and V1 plus V3 is V2 plus V3, then V1 is V2. Okay. Now, let us first see how we do this in Rn. So, let us try to recall how we do this in Rn. So, in Rn what do we do? So, in Rn what we do is, let me do it for example in 3 R3. Z1, Z2, Z3 plus Y1, Y2, Y3. So, how will I conclude that x1, x2, x3 is the same as Z1, Z2, Z3? Well, what I will say is this means x1 plus y1 is z1 plus y1, or more generally xi plus yi is zi plus yi, where I is between 1 and 3, I is 1, 2, 3. And then from real numbers, I know that xi plus yi is zi plus yi implies xi is equal to zi. How do I know that? Because if you add minus yi on both sides, then indeed what you get is xi is zi. So, you can subtract yi from both sides, subtract yi from both sides. Okay, so this will imply xi is zi. And from here we conclude that x1, x2, x3 is the same as z1, z2, z3. Okay, so this is how we do it for real numbers, sorry, for R3 or in general for any Rn. So then let us see how to do it. I mean, we can use the same idea to do it for general vector spaces. So, V1 plus V3 is V2 plus V3. So, this was the argument in Rn. Okay, so now we are given that V1 plus V3 is V2 plus V3. This is argument for general vector spaces. Plus V3 is V2 plus V3. Well, one of the axioms told us that for V3 there exists some V3 prime such that so there exists V3 prime such that V3 plus V3 prime is 0. So, what that tells me is V1 plus V3 plus V3 prime is V2 plus V3 plus V3 prime. But now we know that addition is associative. So, I can write this as V1 plus V3 plus V3 prime is V2 plus V3 plus V3 prime, which implies that V1 plus 0 is V2 plus 0, which implies V1 is V2. Yeah, so this proves the statement here. So, notice that all I used was the axioms. Yeah, I did not use any other thing, any other information about the structure of V, because really I do not know anything else. Yeah, the only things I know are the axioms. Okay. So, whenever you want to check something for a vector space, you have to use the axioms. But to get intuition about whether it is correct or wrong and how to go about a proof in case it is correct, you should look at Rn, see how you do it in Rn, and then sort of extrapolate that idea for general vector spaces. Okay. So, here is a corollary of the cancellation law, the vector 0 described in 3 is unique. So, remember one of the axioms was that there is a vector called 0, yeah, but maybe there are many vectors satisfying that same property. So, this corollary says you can't have many vectors, and here is another corollary, namely that if you looked at the vector v prime, this was in axiom 4, which, so this axiom 4 is what we used in order to conclude the cancellation law by looking at v3 prime, right. So, the vector v prime described in 4 is unique, and it is standard to refer to it as minus v, yeah, and even this reference to minus v will be clarified in a upcoming slide. Okay, so maybe let us quickly do this proof from the cancellation law. So, suppose I have another vector called w such that w also satisfies the same property that v does. So, suppose there exists w in v such that v plus w is v for all v in v, right. This was what 0 satisfied. Okay, but then v plus w is v means what? V plus w is v plus 0, right, because v plus 0 is also v, yeah. So, I can write it like this, but then I can cancel, yeah. So, I am adding v on both sides, so I can cancel v. So, the idea is here you add v prime, right, and so that leaves us with w0. So, cancellation means I can do this, that leaves us with w0. Okay. So, the vector 0 is as described in the third axiom is unique. Okay, and similarly the vector v prime described in 4 is unique, and so we have v plus v prime is 0. So, now suppose v double prime also satisfies this. So, then v plus v prime is 0 is v plus v double prime, okay. And now you can use cancellation. So, cancel v and therefore v prime is equal to v double prime, okay. So, that's the proof of this corollary from the cancellation law. Fine, let us look for some other properties. So, in any vector space V, the following statements hold true. 0 times V is 0 for each V, minus C times V is minus of CV, and that is the same as C times minus V. So, what is minus V? Minus V is exactly the vector V prime which was described in axiom 4, and our previous slide told us that it is unique, and hence we can refer to it as minus V, because we know that that is a vector, so that when you add it to V you get 0. Okay. So, C times 0 is 0 for each constant in R, each scalar C in R. So, let us try and prove this. So, what I can do is I can look at 0 plus 0 times V, and one of the axioms tells me that this is 0 times V plus 0 times V. On the other hand, 0 times V is 0 plus 0 is exactly 0. So, this is 0 times V, right. So, what is the net result? The net result is that 0 times V is 0 times V plus 0 times V. So, you can write this as 0 times V plus 0 is 0 times V plus 0 times V, cancel 0 times V, and that implies 0 is equal to 0 times V. So, that gives us the result, okay. And then we have minus C times V is minus CV is C times minus V. So, how do I get this? The idea is exactly what we have done above. So, we have C plus minus C times V is C times V plus minus C times V, but on the other hand I know that this is 0 times V, which we have just proved is 0. So C times V plus minus C times V is 0. Yeah, so that means minus C times V satisfies the condition required of the negative of CV. Okay, so this implies minus C times V is minus of CV, and then similarly you can check for C times minus V. Okay, finally we have C times 0 is 0, and maybe I leave this to you because it's in a very similar spirit to what we have done earlier. So check this. Fine. So let's do an example sort of from, so to say, from real life. This is an example that we have seen in the previous video, the example of stock taking. So what do we have here? We have stock taking in a grocery shop. So we have 5 items: rice in kg, dal in kg, oil in liters, biscuits in packets, and soap bars. Okay, and the first column describes how many of which quantity is in stock. The second column describes the demand for each product for buyer A. The third column describes the same thing for buyer B, the fourth one for buyer C, and the last one describes what is the new stock that has arrived. So what is, I mean, we did vectors in this context by looking at the corresponding column vectors and so on. So, but we can also think of this as a abstract vector space. So what is the vector space showing up here? So the vector space is the quantity of rice in kg, the quantity of dal in kg, the quantity of oil in liters, the number of biscuits or the number of biscuit packets, and finally the number of soap bars. Yeah. So it's this set. Okay, and so the claim is that this is a vector space. Why? Because if you add coordinate wise, and what you get is so if you have two vectors in this are added, you get the total quantity of rice within those two vectors, the total quantity of dal in kg, the total quantity of oil in liters, the number of total number of biscuit packets, and the number of soap bars, total number of soap bars. Right, that is how you do addition, and scalar multiplication is coordinate wise. Okay, so it so happens that this vector space looks very much like R5. Okay, and why is that? Because we have 5 quantities. Okay, and of course here now once we write it like this, we have to also ask what does one mean by negative quantities and negative number of soap bars. So this again we saw in that example what negative corresponded to. So negative corresponded to demand and positive corresponded to supply. So negative corresponds right. So for example, if you have minus 2 kgs of rice, that means that there is a demand for 2 kgs of rice, right. And if we say that there are 3.5 liters of oil, that means there is a supply of 3.5 liters of oil. And then we can use this plus and minus in order to take stock. This was exactly how we did it in that example. Okay, so of course one has to also interpret things like what is half a biscuit packet or what is 1/8 of a soap bar. So one of the things that we do as a result is that we often express them in units for which we can have any real number instead of only natural numbers, right. So then it seems more natural. So for example, if instead of biscuit packets we had written 100 grams of biscuits, if we know that let's say one biscuit packet is 100 grams, okay, or if instead of soap bar we had written 400 grams of soap, yeah, then there is no issue with decimal places or what we add and subtract. Okay, so this is another example of a vector space, and maybe we'll end with this example of affine flats, which we are going to see again later. So suppose we have so this is a slightly geometric view of vector spaces and a deliberately convoluted one, so that I want you to sort of also be comfortable with the geometry involved here. So yeah, maybe before I start the example I should point out that much of what we did was formal algebra, but behind the scenes there is geometry which is guiding our algebra, right. Whenever we say R3 or R2, in our mind we have geometry, yeah, we understand 2-dimensional space or 3-dimensional space. Okay, so suppose V is a plane parallel to the xy plane, so we are going to define an addition and a scalar multiplication of points on V. So scalar multiplication is going to be done as follows. So let Q belong to this plane and let C be a constant. So we project Q onto the xy plane, scale the resulting vector by C and project the result back to V. Yeah, this is the procedure for doing scalar multiplication. So what is C times Q? C times Q is the tip of the obtained arrow. Okay, this is the procedure for scalar multiplication. Maybe let me draw a quick picture here. So here is your plane, here is your point. So drop this perpendicular to the xy plane. Okay, and then draw this line here, and then if you want to scale this by C, so if you scale it by C, then that means we are going to get some new vector, something like this, and then project this back up to the original space. So you will get maybe something here. Okay, so this is your point Q and this is your point C times Q. Okay, that is scalar multiplication. Okay, so here's how you do addition. Okay, and we are going to watch this addition. This is thanks to our support team. So here's your plane which is parallel to the xy plane, and now we take 2 points on this plane which we want to add. So now we draw our usual vectors, okay, and then we project this down, okay, and now, so now this is in the xy plane. So in the xy plane we know how to add, because that is exactly R2, that is the parallelogram law. So you use the parallelogram law, add them, and then you project the entire thing back to your original plane that you are working with. And now the newly obtained point, which you can see over there, is the sum. Okay, this is the way you add. So I hope the video showed to you the geometry involved in things like addition. So now the question is, so we have defined what is scalar multiplication and addition on this set, and now I will leave you to check that this is a vector space. You can either do it geometrically, or better to do it both ways. So try to think of geometrically by visualization why this is a vector space, or you can just write down the algebra and work out that this is indeed a vector space. So in either case, what can help you is the following. So the idea behind the addition and multiplication, scalar multiplication here is that really you are looking at vectors. We are taking points, drawing the corresponding vector, but then remember that you project down, right. So this is essentially what we are doing is we are looking at arrows which start at the point where the z axis intersects this plane, and where the tip is the point you are interested in. Okay, so you take those kinds of arrows, and then you do addition and scalar multiplication for those arrows exactly the way you do it for R2. This is really at the heart of what's going on. Okay, so I'll leave that visualization to you, and I hope you can see that this is indeed very similar to what we do in R2. Okay, so let me summarize what we have seen in this video. So in this video we saw, we began by seeing the some more properties of vector spaces, in particular things like how the zero vector behaves and how the negative of a vector behaves, and so on. We saw somewhat real life application of vector spaces, namely we took our good old grocery shop problem and saw how vector spaces fit into that context. And then we have seen the example of affine flats. Thank you.